It's my pleasure to be here with you today to share our work in a collaborative project between Queen Mary, University of London, Sorbonne University, and EPFL in Switzerland. The project is very much in line with the introduction Martin gave to the workshop. So we are sharing information across sensors to be able to understand what's going on in a scene for a robot to take decisions. This project, CORSMAL, is about two communities getting together: the community of computer vision and signal processing, together with the robotics community, in order to enable tasks that are very challenging today. And we are using AI and robotics in order to address a relevant task. In particular, in this project, we are interested in recognizing objects that were previously unseen by the robot, so that the robot can grasp them, manipulate them, and place them somewhere. We are using multiple perception modalities in this project: vision, sound, and touch, in two different moments of our scenario. When a human is picking up an object and interacting with that object, and then when the robot grasps the object and manipulates the object in their hands. Because this is a very challenging topic, we are also providing our data, our models, and our protocols to the community. And we organize challenges around these tasks. And now the community has started picking up what we have distributed, and they are themselves developing new models. So the core of this presentation is about the recognition of objects that were unseen by the robot. So we're not using any known models of the objects for robots to understand what are the physical properties of these objects to be grasped, manipulated, and then placed somewhere. So the specific context we have been designing is one where we're using household containers, so objects of different sizes, shapes, and transparencies, which might contain content, and the content is unknown to the robot. So both the type of object and the content of this object is unknown by the robot, and the robot has to understand the physical characteristics of these objects by observing the human, by observing the actions of the humans, and then by correcting the grasp once the object is taken by the robot itself. We split this problem into three main phases. The first one is when a human approaches the object and start manipulating it, and then the dynamic handover towards the robot. Here you see a gripper, but part of the project is also dealing with a robot hand. And finally, the robot places these objects in a specific place in the environment, with the goal of making sure that the object is not modified and the content of the object is, if any, is not spilled. So we have primarily three phases: so the human manipulation part, the dynamic handover towards the robot, and then the robot manipulation and delivery. In terms of sensing modality perception, we are using vision, either single view or multi-view vision, sound information from an array of microphones, and touch. And I will mention later on why we're looking at touch also on the human side. And finally, once the object is in the grasp of the robot, we are using tactile information as well as sound to make sure that the robot can react to the movement of the content within the object itself. So let's give a brief overview of a few methods we have developed for the recognition to prepare for the grasping. So we have been looking at people manipulating those objects, and not only looking through vision, but also listening to the sound. I'll try now to play. Being pulled inside a cab, and what we are trying to do is to estimate the amount of filling, and hence to understand the weight of the object by listening to the sounds in the environment. So we developed tools for sound-based classification of the content level and content type in a container. We made those models available to the community, and the community can now use those models for their own pipelines. Then we looked at the filling level only from a vision point of view. And as I will mention later, we will use transfer learning based on adversarial training in order to tackle the problem of limited training data set we have for this specific task. Because AI and robotics is very much reliant on robust models, we have been looking substantially in the project at the robustness of this model, and found that redundant features can be detrimental to the ability of robots to adapt to other environments. We also look at how to estimate the shape of objects when these objects are transparent, and therefore very, very challenging for a robot to understand and to determine the properties of those objects. And I will show some results of this later on. Going back to what I mentioned earlier, so the use of tactile information for humans, we observe how humans are interacting with these objects because we want to provide the robots with the ability to predict the properties of the object by looking how humans are handling these objects. And there are a number of results on observing human grasping behaviors and how this grasping behavior and the action of giving an object to a robot or to another human is suggesting information about the physical properties of the object. So we're using tactile sensing both on the human side to characterize behaviors and to model behaviors, and on the robot side to adapt the grasp once the object is grasped by the robot. Let me also describe one of the initial outcomes of this project, which is the definition of a benchmark where we are considering both humans and robots in the definition of performance scores that allows us to compare different methods. So we defined a set of scores for the perceptions prior to the handover, then a set of scores for the robot, and finally global scores for the full task. This set of scores and the protocol for benchmarking were described in a RAL paper, where we define what the CORSMAL benchmark is in order for methods that are working on this scenario to be compared, and therefore to facilitate improvements of these models. Among the various aspects that we define within this benchmark, we have how to grasp the objects in order for the methods to be reproducible. So we defined a set of objects that are available worldwide, and we define how subjects passing on these objects to the robots should handle the objects in order for experiments across different laboratories to be comparable. In this case, we have different types of occlusions and different places where the robot can grasp the object that is passed over. So this is one of the several definitions we have for the benchmark, and we hope this benchmark will be of interest to some in this workshop to replicate the results we have already provided. And so these are examples of the baseline code we have developed for this task. So we have a human. A robot has never seen that object before, hasn't got information about the weight of that object, nor about the material of that object. And it's observing the scene through two cameras on the side of the robot, and is observing the movement of the person to track where the object here we have only information about the general category of the object, not the specific instance. And through local segmentation and triangulation, we can localize where the object is over time. If you are interested in this pipeline, we have the code enabling what you have seen in the previous videos available in GitHub, and also the description of the benchmark, the objects, and how to develop these methods in order for you to compare with existing baseline results we have provided. Moving on from the benchmark, we have also developed a number of tools that are available open source. This is in particular something we have recently presented at ICIP 2021, and it's about the ability of a robot from a snapshot to understand the filling level of a cap. Here the problem is particularly challenging because, as you see, you might have various environmental conditions and also different levels of transparencies. We have only a data set with 10,000 samples, and therefore we are limited in the ability of training. And therefore we were interested in understanding what are the best strategies for going from a source domain with a large amount of data, like for example ImageNet, to the target domain, which is our target domain of filling level. So we investigated several approaches, and what we found to be the most effective approach for this task that has got a limited amount of data in the target domain is using adversarial training in the source domain and then fine-tuning in the target domain. For those of you who don't know what adversarial training is, adversarial training means training a model using adversarial examples, which are sample data that have been modified to induce the original classifier to fail in its classification task. So using a source domain, in this case ImageNet, through adversarial training, meaning using adversarial examples for training, we started the source domain with this type of model, and then the model is refined on the smaller data set for the specific task. And we showed how, using this approach, it is possible to improve the classification performance in our case and in our specific task. The models we have created for this are available open source. So if you're interested, you will find them in the CORSMAL website. In addition to models, we have distributed a set of data sets as well. This is a starting data set for people to get a grasp on the type of data we are interested in. You see on the top a set of different transparent container, and then going down you have translucent and opaque container. And we also distribute a model for you to be able to localize the object in space and determine their shape. This is based on stereo vision, and in particular on localizing the object of interest in the frame, and then through an iterative multi-view shape fitting approach, we are moving from 2D to 3D and trying to refine the estimation of the shape. So you see there at the middle the centroid X, through which an axis is defined, and then a set of circumferences are slowly getting to converge towards the actual shape of the object, and the fit into that shape is controlled by reprojection on the camera view. I will now show some examples of this fitting approach, which is the starting point for people then to be able to determine the shape of objects prior to the grasping. And again, I'd like to stress that here we are not using any prior information about the object. We don't use any prior 3D models. We don't use any specific instance information about the objects we are looking at. In this specific case, we assume that the object is symmetric around its main axis, and you're seeing that different shapes are catered with the model we are using here, with its projection back and forth between 2D and 3D. The next data set we have developed and is available out there is the CORSMAL container manipulation data set, whereas instead of just having containers on a tabletop, we do have a human manipulating those containers and their content prior to passing those containers on to the robotic arm. We have collected data from 4 cameras, one of which is worn by the person giving the object to the robot, and also the sound produced by the manipulation of the object and its content. Those data are available, and I can give you some examples here with sound. So I will now stop talking for a while so that you can hear the type of sounds that have been collected for this data set. So these are a series of scenarios that have been collected. And the idea is for AI perception to be able to understand through the movement of the person, through the appearance and the sounds of the container and the content, to understand what are the physical properties of this object. And in particular, for the CORSMAL challenge, we have identified 3 initial tasks, which are determination of the filling level, the filling type, and the container capacity estimation from the audio visual data in order for methods to be able to estimate the mass of that object. And we have 2 additional tasks for the most recent version of the challenge, which is the estimation of the mass of the container and the dimensions of the container. In particular, we are looking at the height and the width on the top at the bottom of the container. So these are the tasks that we are aiming to satisfy for the robot to understand what are the forces to apply, what is the size of the object to grasp prior to the dynamic handover. Baselines for this are available, and I'm very pleased to announce that we have had this CORSMAL challenge accepted as a grand challenge for the international conference on signal processing, which is called ICASP, in 2022 in Singapore. If you decide to participate in this challenge, you will have availability of a large number of baselines and existing methods and their previous results, so you can compare with. If you're interested in the dataset and the rules of the challenge, this is the link. And I do hope that a number of you will be interested in this CORSMAL challenge. In summary, I'd like to show what are the main outcomes of this project, CORSMAL. So we define a benchmark and a number of benchmarking baseline algorithms for human to robot handovers. These algorithms have already been used by the community, who have already started publishing results in this. So on the bottom left, you see the scenario where you have a subject and a robot, and 3 areas where you can hand over the object. And we define a protocol for people to be able to replicate these experiments. And experiments with a human in the loop are very difficult to replicate. And therefore, we've been very careful in defining a protocol that would allow us to meaningfully compare results across laboratories. The CORSMAL protocol and code are available in GitHub, and the description of the benchmark is available on IEEE Explorer. We are disseminating 2 datasets, and a 3rd one with haptic data is about to be distributed as well. You can see the CORSMAL container dataset at that URL, and the CORSMAL container manipulation dataset at the 2nd URL. So I invite you to have a look at those data. Those data are multi-sensor, multi-model data, and allow a robot to understand what the properties of the object is without having any prior models. Models are pre-trained and are available at the link you see in there, and are part of some recent publication. And importantly, we have now a platform that is open, and people can submit their results for the CORSMAL challenge. And the advantage is that they have quick access to results that have been generated by other competitors, and therefore comparisons are made easier. We have developed an evaluation toolkit for you to be able to take the results and compare them in the testing set. And importantly, you will have available the entire pipeline, whether you're using a robot or a simulator. And to this end, we have also developed a simulator for you to be able to test the results without direct access to the physical robot. With this, I'd like to close and summarize the main outcomes of this project to date. So we have defined the benchmark for human to robot handovers and a series of evaluation protocol and toolkits. We have developed new models which we made available, and also new data sets that are part of the challenge. I'd like to thank the partners of this project, in addition to Queen Mary, Sorbonne University, and EPFL, and the sponsors, which are the national funding body. I hope that you will be excited by the challenges in AI and robotics associated to this problem, and that you will join the CORSMAL community and the challenge. Thank you very much for your attention, and I'll be happy to answer your questions.
Thanks a lot, Andrea, for this very nice talk. Let me have a look at the chat. Yeah, so there is one question from Gregory Roger. Thanks, Andrea, for the nice talk. Could you please comment on how you handle possible safety issues for experiments on human to robot handovers?
Yes, thank you, Gregory. We have identified 3 types of safety issues. So from the simplest to the more complex, we have the safety issue for the object, then the safety issue for the robot, and most importantly, the safety issue for the human. So as far as the robot is concerned, you saw that in the case of the data set, we avoided using water directly on the filling, and therefore we have a number of data that are recorded with rice and pasta, but not with water. We had long discussions regarding that and what could happen in case of problems with the robot. The most important part is, of course, the safety of the operator. So the way we have defined the protocol is that the robot is on one side, the human is on the other side, and we are using robots that are safety compliant, and therefore they would not apply more than a certain level of force, and they are very reactive. Plus, we have all the protocols that usually are applied with the safety button and the observer during the handovers.
So, if I can follow up, so this means that for this experience, yeah, especially in practice, you would use like safe cobots or so, in a small scale robots that cannot harm the humans, essentially.
We have the robots you have seen in the pictures and in the video, but we are using robots that have got safety control on board, and also for those, let's say, when the method is not ready yet, we have developed a simulator for CORSMAL, which is available to the community, and therefore the idea is that you first develop your tools through the simulator, which exactly replicate the benchmarking conditions, and then once they are robust enough, they can be moved to the real robot.
Okay, very good. Thanks a lot. I had a question about the data sets you mentioned.
Yes.
This consists of multiple objects. I missed probably the part. What are these objects provided with a 3D scan, or what is exactly the data looking like?
Actually, one of the goals of the project is really not to use that type of information.
Okay.
We provide the purchasing links of these objects, and at the time of definition of the data set, we try to make sure that those objects were widely available through Amazon in the world. And the idea is indeed to use only perception, to be able to recognize the environment, recognize the behavior of the human, and recognize the specific object. And then, for example, like in the case I showed earlier with the iterative approach between 2D and 3D, try and progressively estimate the shape and physical properties of the object for the robot to be able to plan the grasp and then to adapt the grasp when the grasp was started.
Okay, thanks a lot, Andrea. Are there any more questions? Find my Zoom.
See, there is a question.
Yes. Do you see the question, Andrea?
Yes, I have it in front of me. So, yeah, good point on the reproducibility of the results for other catching tasks. We spent quite a lot of time defining that protocol because we were very worried at the beginning that because of the humans being part of the pipeline and different robotic arms, we might just end up with a wishful thinking list of subtasks to complete. And therefore, we really reduced the possible variability within something we believe to be acceptable for the reproducibility of the experiments. In the case of the catching task you're mentioning with the ball, I think that perhaps one should rethink the protocol in terms of the overall task, in terms of the ability of recognizing the properties of the object. I think most of the scores could be reused. They should be reassociated to the specific case of, in this case, an object on the fly, as opposed to having an object that is partially occluded by the hand. So at a first glance, I would say the exact scores, most of the exact scores would fit. In our case, we have some specific scores for the spilling of the content of the object, so that case would not be appropriate for catching a ball. But I think that most of the scores, in particular the perceptual and the global ones, would be reusable for another set of tasks like the one you mentioned in your question.